In this lesson, we'll do a very brief tour of the entire universe and the history of the universe. In this picture here, we see from a science magazine the Big Bang Theory. On the left, we have the origin of all matter and energy and time and space in our known universe in this colossal Big Bang. As you move to the right, time is elapsing and things are happening. So the universe is expanding, and in time it will cool enough so that little particles can emerge from the flux of energy. These subatomic particles will form the first atoms, like hydrogen and helium atoms, and then these giant clouds of hydrogen and helium will coalesce to form galaxies, and within those galaxies, stars. So the stars we see in the sky, the splotches of light, which are galaxies that we see in the sky today, had a long history. Now, there's a lot of evidence for this Big Bang Theory. One of the pieces of evidence is the observation that galaxies in our observable universe appear to be moving away from each other. It's not that all the galaxies are moving away from our own. It's that ours, too, is moving away from all others. And one way to think about this, or an analogy for this, is to imagine that all the galaxies in the universe are sort of painted on the surface of a balloon. Now, if you blow up the balloon, all of the galaxies will be moving away from each other. So in a sense, there's no center of the universe. All of the galaxies are moving away because the space in between them is expanding. And so this idea of the expansion of the universe suggests that at some point in the past there was some origin to the whole thing, and that's known as the Big Bang. Now, we're going to simplify the story here and indicate here's the Big Bang, the explosion of all matter, energy, space, and time into existence around 14 billion years ago. Over time, as the universe expanded, it cooled. And as we saw in that first diagram, as the universe cooled, the energy could start to sort of convert into little particles, subatomic particles, that assembled themselves into the first atoms. Now, which atoms got made? Well, the universe today consists mostly of hydrogen and, to a lesser extent, helium. Well, these are the two simplest kinds of elements. The atoms are the simplest atoms of all the elements that we know of. Well, what happens to a cloud of hydrogen? Well, hydrogen atoms have mass. All objects with mass attract under the force of gravitation. So a cloud of hydrogen will begin to condense. And as that cloud condenses under the influence of gravity, it will get hotter and the pressure will increase. And at a certain point, the hydrogen nuclei will be smashing together with such force that they will fuse to form helium nuclei. And energy is released in this reaction. This is nuclear fusion, and this is what makes stars shine. The energy from this fusion reaction we detect as light and heat. Now, that sets up a situation where that fusion reaction tends to want to make the star sort of expand, but gravity is that counteracting force, and so you get this sort of balance of forces, and we have a stable star. Now, inside the core of the star, as we've just seen here, hydrogen can fuse to form helium. Well, those are two different elements. As the star goes through its fuel, it will start to create even heavier elements, heavier than hydrogen and helium. So the carbon, the oxygen, the nitrogen, those types of elements are forged in the cores of stars. But what about the even heavier elements? Well, scientists have figured out that what happens in the formation of those elements is that a star will explode, forming the even heavier elements. Now, why would a star explode? Well, simply put, the star is going to run out of fuel, and if it runs out of fuel, this red arrow, that fusion sort of force is going to be diminished, and gravity will win that battle, and the star will get compressed even more, and then the star is going to explode. Now, when the star explodes, the temperatures and pressures are sufficient to generate heavier elements, and these elements are ejected into space. Now, what do we mean again by heavier elements? It's just heavier elements have more protons in the nucleus of the atom than lighter elements. So here we see hydrogen, helium, lithium. They differ by the number of protons in the nucleus. We're not showing the neutrons. Neutrons are those particles that keep the protons together. Protons have a positive charge, electrons have a negative charge, and there's an electrostatic interaction here, and that kind of keeps the atom together. So atoms are electrically neutral. However many protons there are in the nucleus, there are equal numbers of electrons orbiting. Now, this is a simplification of what an atom is, but we can just get the basic idea that atoms differ in the number of protons in the nucleus of the atom, and as you have more and more protons, we would say the element is a heavier element. Remember, an atom is the smallest unit of an element that has the characteristics of those elements. Now, what's going to happen to those heavier elements that were formed from some exploding star? Well, they're going to be ejected back out into space, but they may then mix with some nearby cloud of hydrogen. Well, this cloud of hydrogen, under the influence of gravity, was about to form its own star. Well, now we have some heavy elements from a nearby star in the mix. And as lots of these clouds have some rotational movement while they're kind of collapsing, so too then will the heavy elements that are mixing with that cloud. So what you'll have here then is a star forming at the center of this system, and you'll have the heavier elements accumulating into dust and then into small rocks and then bigger rocks, etc., to form planets. And so today we have the inner planets shown in this diagram, with the Sun, Mercury, Venus, Earth, and Mars orbiting the Sun. So we can think of this process then as one in which planets can trace their origin back to stars. Stars created the heavier elements out of which planets are made. So when we look at the night sky and we see those clouds and we see stars and such, we want to think about this material out here as being mostly hydrogen and helium, capable of forming new stars, but mixed in would be heavier elements from the explosions of other stars, previous stars. So we have the future possibility of new solar systems forming in these giant clouds in our galaxies and in galaxies throughout the universe. Now, the Earth, initially in the formation of our solar system, would have been lifeless, no life here. And so for people studying the origin of life, of course, the question is, how did life take hold on planet Earth? Well, one consensus idea in the scientific community is that there was some important chemistry going on the early Earth. Chemistry that produced lots of interesting organic molecules. And these molecules then assembled into the first life forms, the first earliest cells. Interestingly, organic molecules have been detected in space, in some of these clouds that you see through telescopes. In addition, meteorites that have impacted Earth have had amino acids and lipid molecules and sugars, etc., in them as well. So evidently, significant chemistry can be going on in outer space, not to mention the chemistry that might have been going on in the early Earth.